So in the previous lecture, we have discussed how this simple three sorting techniques, sort, selection sort, or insertion sort, or algorithm can be implemented. Now in this lecture, we'll see how this is done. The computation complexity is three things. So, what's basic video and square basic is complexity about subject order of n square. The average is also order of n square. What are the best case and the worst case? I discussed in the previous lecture that worst case is the scenario and that is sorted in reverse order. That we need to sort in ascending order, but least is sorted in descending order. So this is the best case scenario. Worst case scenario. The best case scenario is that when the disorder is same order. That is, we need to sort in ascending order, and the list is already the input list is already sorted in ascending order. So, well, that is the best case scenario. The worst case scenario is that in the list is in random order, and we need to sort it in ascending order. So the worst case complexity of bowels and is order of n square, best case also order of n square, and best case also order of n square. And we'll see how this the algorithm will simply compute how this order of n square is done. So for selection sort, also the worst case scenario for order of n square, for best case scenario also order of n square, and for average case also order of n square. But in the selection sort, the worst case is order of n square, best case is order of n, and average case is order of n square. So we'll see why this best case scenario is order of n in insertion sort. So from the to the implementation of bubble sort, for simply assessing any algorithm, what we can do that we count the number of nested loop. What is the number of nested loop? Where the number of nested loop is 2, and the first loop is dependent on n, and it is from n to 1. That is it dependent on n, and the second loop also from 1 to I minus 1. So it is also dependent on the n. So the order is n into n, that is order of n. So simply you can see from seeing the nested loop in the algorithm, the order of the algorithm. But if we want to find it more accurately, then you can see that when I equal to n, this inner loop, that is this swapping and comparison, will work from 1 to n minus 1. That is, this comparison and swapping step will be performed n minus 1 steps. Then n reduced to n minus 1. Then these steps reduced to n minus 2. So next iteration will be performed n minus 2 steps. In the third iteration, it will perform n minus 3 steps of comparison and swapping. Equal this to n. So if take this sum of natural numbers, the simple formula n into n plus 1 is n minus 1. N minus 1. So it will be n minus 1 into n. So from this expression, this the highest term is so come the x square. Order will be so this implementation of also the complexity is simply is square. Similarly, then we'll see what's the scenario. So what is the worst case scenario? The worst case scenario, if it is something element, then if the Scorpion comparison will make the same number of operations. In the worst case, will be also the next one. And also in base case, the base case, if all the if the list is already in sorted order, there also in India this swapping and comparison operation, all the swapping operation. We need to. So in that case, it also be uh, order of n square. But this scenario of order of n square, order of n square, it can be reduced to order of a. It is to order of a. How? Because if it is already in sorted order, then if we perform this swapping operation, then neither in the one poison there will be any swapping. Because if it is already in sorted order, if it is like 1, 2, 3, 4, 5, like list is already in sorted order, and we perform this comparison, then in every comparison there will be no swapping. But if one pair are all in ascending sorted order. So in the first iteration, the last state we into the file, but technically no swapping. So in base case, if we check the number of swapping, that if there is no swapping, then we stop the then it can be in order of n. So after this execute file, if we just add a flag pause, and in this swapping after with this swapping section, and we update this flag to that is if one of the swapping operation is happened, the flag become true, and we put a condition block that if flag is true, if flag is true, we take from the break from the outer. So in the best case scenario, if it is already sorted, there will be no swapping, and this flag will be like will be false, and we break from the this algorithm, so it will become order of n. So this best case scenario of outshot can be reduced from order of n square to order of n. In the next slide, we will see what is the complexity of selection sort. So the next is selection sort. What complexity of selection sort? So where we will see that there are also two nested form from B. We say that similarly, similar to the vowel sort, it is also the order of n square, and it's best case, worst case, and this case all are complexity of order of n square. Because if the element is already sorted in sorted order, what to be was fine. But the checking of the finding finding the maximum element that is traversing the list. This will happen in this case also. So every time it will traverse and traverse the list, and find the maximum element and put it to the right position. Then the remaining unsorted list, right? Let's say, and it is perform the same repetitive operation for the list. So in the previous slide, I discussed that best case scenario of insert can be reduced to order of n squared order of n using a plan. So here also in the selection sort, the best scenario we can reduce to order of n using a flag in this section where the flag is changed. We must initialize flag something 0 or 1 in number. Then we update this flag in this section. Then if the list is already in sorted order, then if it travels for finding the maximum element, it will find the maximum element in the last position. So uh, for the storage location which is storing the maximum element and the traversing all the elements, there will be no swapping between. So there will be in the index. Sorry, there will every time there will be a change in the index because the last position in the maximum position. So every time its traverse maximum position will be changed. So this finding this maximum numbers index, it will perform n times. So if we put flag equal to flag 1, that every time initially put flag equal to 0 and we thus put this in pivot state, and we can this in block every time it change the index of finding the maximum element, the flag will decrease, and finally flag decrease. And we will even aim for a already sorted list. So we can check here and that if the flag is equal to 1, sorry, if flag is equal to n, then we can uh, take the loop and escape from the outer loop. So don't need to execute down from it 1 in the first direction. We can decide that the list is really sorted. So we don't need to perform other steps of the loop. Likewise, this we can reduce the best case complexity of selection sort into from order of n square to order of n. Now, in the next slide, we'll see what is the complexity of insertion sort. So we have seen that insertion sort complexity in the average case complexity is order of n square. Worst case the order of n square. The best case is order n. So for normally with the implementation power, so that selection so as the complexity best case complexity order of n square equal. But with the this implementation, best case complexity of insertion sort for the order of n. Why this is order of n? Because if the already if the this is already in sorted order, then if it is already in sorted order, then every time we try to insert the next element of the sorted sub-list, we will don't need any sorting because it is in the right place. So every time we insert, if we want to insert from 3 into 1 2, it will be the right position. Then it will remain in the same place. If we want to then insert 4 into the right position of the sort is 1 2 3, 4 position is the right position. So there will be no swapping. So in this case scenario, if the list is already in sorted order, there is no need of this while loop will not execute. No need to execute this one. So only the outer loop is executing n times. The best case scenario, the order of complexity, the complexity is order of n. So from this approach, it is the insertion sort is has the advantage over bubble sort and selection sort. That is best case complexity is order of n. And there is only to add any other condition, no to use any flag or change this. Second, this simple limitation is uh, performing best case scenario in order of n. So we have seen this worst case, best case, average case implementation on its complexity and plus the space complexity of these three implementation. And we have seen this all these three implementation. We have only one list storing the input data, no other no other so use only one temporary variable is swapping. So there is no extra the storage needed that is dependent on the input size. So for all the three cases, the space complexity is order of 1. So this is the end of this lecture where I have discussed three basic comparison and swapping based algorithm, bubble sort, selection sort, and insertion sort. And we have seen comparatively what are the different approaches and what is the different between three approaches. And, what is the advantage of this one over this one? So in the next lecture, we'll see the other approaches of sorting algorithms, which is not solely based on the comparison and sorting. There are sorting algorithm which is approach divide and conquer, like in merge sort, quick sort. There is sort like heap sort. There is the trees data structure. So in the next lecture, we'll go through this advanced sorting algorithms, which are different from these three basic swapping and comparison based techniques. And we see what are the disadvantages of these three techniques and what are the advantages of those advanced techniques using divide and conquer over this comparison swapping this basic sorting techniques. Thank you. This is the end of this.